Alright, so capacitors in series and parallel. So we learned about capacitors last lecture, and now we have all of the basic building blocks of circuits, and we talked about how things combine in series and in parallel. Series and parallel. So you might be wondering how capacitors combine in series and parallel. So it turns out that it's opposite from resistance. So to get right to it, capacitors in series, here I'll just write series, they combine in the same mathematical way as resistors in parallel. So 1 over the equivalent capacitance is equal to 1 over the capacitance of the first, plus 1 over the capacitance of the second that's in parallel, plus 1 over the, that's in series, 1 over capacitance of the third that's in series, and so on. Alright. So this is one of these things that's easy to get mixed up on. So just do enough practice problems where you're using each of these formulas, and hopefully your brain will kind of sort it out after a while. But I'm going to give an effort to explain why it is like this, instead of just presenting you with this odd kind of, reversal here. Hopefully between that and you doing a few practice problems, you'll be able to sort it out. Okay, so let's say we have two capacitors in series. So this will be our first, this will be our second, right? And then I'll just call these point A and point B. We won't connect them. So this will be A, this will be B, and we can identify a point C here in the middle. Alright, so there's some total potential difference of the whole circuit section here from A to B, right? So the potential difference across from point A to point B across or through both of those capacitors in series. And we can also talk about the potential drop for over each of them, right? And so there's some potential drop here, or potential difference I should say, not necessarily always drop, right? And we can call this one VAC, because that includes that capacitor 1, call this capacitor 2, and this is going to be VCB, right? So these potential drops, remember, they're just, our potential hills, so to speak, right? So depending on the circuit component, it could be an uphill or downhill, or, if nothing's going on, then it's just flat. All right, so I'll call this top one V1 and this bottom one V2. Okay, so we can think about how these things add by thinking about how voltage adds in a circuit. There's a garbage truck there. I don't know if you guys can hear it, but it's pretty loud. Alright, so we have VAC being equal to V1, which would be equal to Q over C1, right? If you think about the definition of capacitance, you will agree that that is a correct expression. And we have VCB being equal to V2, and likewise Q over C2. Right, so the way that these two things add to find the total voltage V, or VAB, right across both of these things, which we said was V, you would take V1 plus V2. And so that gives us, if we write out what it is for these capacitors, it would be Q over C1 plus Q over C2, or take that Q out and say 1 over C1 plus 1 over C2, right? And if we're really solving for this total V, right, I'm going to write it down here. V equals, I'm going to bring this Q over and say V over Q is equal to 1 over C1 plus 1 over C2. And that's just if we had 2 capacitors in series. If we had 3, then it would also include a third. That's, 1 over C3 and so on. And V over Q is equal to 1 over the capacitance, right? Looking back at the expressions we have up here will remind us. And so that would be 1 over the equivalent capacitance for both of them, right? This capacitance would account for the charge and voltage of both capacitors connected together in series, the whole situation between point A and point B. And so that's equal to 1 over C1 plus 1 over C2, just like we had before. And that kind of helps you understand why capacitors in series add in this inverse kind of formula. All right, so now capacitors in parallel. So I think I was using purple to represent parallel. So for parallel, we have equivalent capacitance being equal to C1 plus C2 plus C3 plus, and so on. Right? So that's just like how capacitors add in. This is just how resistors add in series, and this is how capacitors add in parallel, right? So let's talk about it again. So if we have the same AB type circuit, but this time we have 2 capacitors in parallel, draw them nice and big here. I'll do it like this, right? It's kind of sloppy. So we have junctions here, right? And so that they're in parallel. The charges can either take that path or this path, but it can't take both. And so these two are in parallel. So we'll call this C1 and this C2. We'll call this Q1 on capacitor 1 and charge Q2 on capacitor 2. We'll give these an A, an A and a B designation. And what we're wanting to find is this total VAB potential difference that's accounted for by both of them. Alright, so the charges on each capacitor, according to just the definition of capacitance, yet again, we can write Q1 is equal to C1 times V, and Q2 is equal to C2 times V. And the total charge of the combination of the 2 capacitors, right? So the total charge of both capacitors that are present here is equal to Q1 plus Q2, right? Which would be C1 plus C2 times V. And so then we move our V over, and we get Q over V, Q over V, which is equal to C, equivalent of the whole thing, being equal to C1 plus C2. So I don't know if that helps your brain kind of sort this out as to why these equations are the way that they are. If it does, awesome. If it doesn't, then it's just one of those where you'll have to know to use the correct one when the time comes. But hopefully that gives you some sort of hint as to what's going on, and at least, have something to grip onto for making sense of this. Alright, so next we will do a practice problem with adding capacitors together, and then talk about our final section.